So let's solve a second order differential equation using Laplace transforms. So we have this guy. Notice we got the constant coefficients on the left. This is non-homogeneous. Notice they've given us two conditions here. So if we apply Laplace transforms, we're going to have to take the Laplace of each piece. So there's what we have. Now, this information came from the theorem on the other page, theorem 722. So let's apply this to this, taking those Laplace transforms. So the Laplace transform of y double prime is going to be s squared y of s minus s times f of 0, and our f of 0 is 1, minus f prime of 0. F prime of 0 in this case is 5. The Laplace transform of y prime, going back here, is s y of s minus f of 0. F of 0 is going to be 1. The Laplace of y is just y of s. And then the Laplace of e to the negative 4t, we're using that table, and this is going to be row 11. It's going to be 1 over s minus negative 4, since negative 4 is our a, which is 1 over s plus 4. So now let's plug everything in. So if we do our substitution, we have the Laplace of y double prime minus 3 times the Laplace of y prime, which is s times y of s minus 1, minus plus 2 times the Laplace of y. The Laplace of y is y of s, equals the Laplace of e to the negative 4t, which is 1 over s plus 4. So we're just substituting all of those pieces in for these 4 items. So let's do some simplifying here. I'm going to combine some like terms, have s squared y of s. I'm going to do some grouping too. I'm going to rearrange just a little bit, kind of grouping all of those y of s terms together. So I've grouped those together. And then we have a minus s minus 2. So these 3 have that y of s in common. If we factor it out, we're going to be left with s squared minus 3s plus 2. And then we have 1 over s plus 4 on the right. And I'm going to go ahead and move that s plus 2 over also. So now we want to isolate y of s. And we can do that by dividing by that s squared minus 3s plus 2. And that guy's actually going to factor. Let's get a common denominator so we only have to do partial fractions once. Let's get an s plus 4 over s plus 4, multiplying that second fraction by what the denominator is missing. I'm going to work with that numerator. That's going to be s squared plus 6s plus 8, which is s squared plus 6s plus 9 over the denominator. So now we get to do partial fraction decomp. We actually did that decomposition in a previous example, but I'm going to work through it just so you can see it again if you need a refresher on partial fraction decomp. So we have s squared plus 6x plus 9 on the left. A needs to be multiplied by s minus 2 times s minus 1. B needs to be multiplied by s plus 4 times s minus 1. C needs to be multiplied by s plus 4 times s minus 2. If I factor out that right, I have s squared minus 3s plus 2. Factor out that middle, s squared plus 3s minus 4. Factor out the last, s squared plus 2s minus 8. Oh, factor FOIL. I think you guys know what I mean. So from here, we can get our system of equations. So I'm going to turn to a new page. I'm going to copy this. So to build our system of equations, we're going to compare some coefficients on the left and on the right. We have a 1s squared on the left. That's going to be equal to a plus b plus c. I have 6 on the left in front of s. It's going to be equal to negative 3a plus 3b plus 2c. And then 9 on the left is equal to 2a minus 4b minus 8c. So if we were to take that and we were to substitute into our matrix, so I get 1 over 30, 25 over 6, and negative 16 over 5. So let's look at how we set that partial fraction up. So we ended up with this guy when we factored. I'm going to copy that and then paste it over here. So then this means our y of s is equal to 1 over 30 over s plus 4 plus 25 over 6 over s minus 2 minus 16 over 5 over s minus 1. So we have solved for y of s. Now we want to take the inverse Laplace. In other words, we want to go back home to the rectangular world, out of Laplace world. So when we do that, we're going to have y of t on the left. So we're going to have 1 over 30 And then we need to take the inverse Laplace of 1 over s plus 4 plus 25 over 6 times the inverse Laplace of 1 over s minus 2 minus 16 over 5 times the inverse Laplace of 1 over s minus 1. So the formula we're using for every one of these, this is going to be row 11 in your sheet, your transformation sheet. Going back to this guy, you can see how that 1 over s minus a matches all three of those pieces for us. We just have to figure out what a is. Remember, it's the number that comes after the minus. That first one has to be rewritten as s minus negative 4. So this is e to the negative 4t plus 25 over 6, e to the 2t minus 16 over 5, e to the t. So there's our y of t. Okay, now I want you to notice in both of these, they are giving us particular solutions. And that makes sense because we have initial conditions in both of these problems. Our initial conditions here are there. And then in the very last problem, we had initial condition here. So we're always going to get a particular solution for that final answer. In other words, we're not going to have any C1s or C2s, any kind of constants in there. In some ways, I think Laplace transforms may be a little easier than trying to solve something using a different technique. Let's look at this one and see what would be another possible approach. So since we had constant coefficients on the left, we could come up with that particular solution, not particular, the complementary solution. So we could solve this by creating that auxiliary equation. So then the complementary would be C1 e to the 2t plus C2 e to the t. So you can see where that e to the 2t and that e to the t are coming from over here. But we had a C1 and C2 in front because we were not to the point where we can apply all of this information. And then we would have to use a different technique to solve the that non-homogeneous piece, which was e to the negative 4t. So one possible way you could do that I think I would go with undetermined coefficients. You could use variation of parameters also, but I think undetermined coefficients might be a little bit easier in this case. So then you would go through that process, figure out what this is going to look like. Our idea would be that this would be ae to the negative 4t. So then we would run with that, figure out what a would be, and then we would create that general solution with yc plus yp. And then once we would have that, then we could plug in the initial conditions to find our C1 and C2. So it's definitely a process to solve. We could solve this a different way using undetermined coefficients. You could probably use variation of parameters too. I don't see why you couldn't. But I think in some ways the Laplace transforms takes a lot of that out for us. It makes it a little bit easier. We don't have to worry about finding C1 and C2 because when we take the Laplace of the y double prime and the y prime, it's incorporating what those initial conditions are within that Laplace transform. The hardest thing we had to do here, honestly, was probably that partial fraction decomposition. So take some time, try a few of these. I think these are fun. Hopefully you'll think the same thing. And if you have any questions, please let me know.